Distributed systems and microservice architectures can be really complicated in terms of networks. When a customer clicks around on your website, there would be many web requests going from the client's browser to your web server. And on the back end, there would be network requests flowing all over the place between microservices, databases, proxies, and more. With the customer clicking around on your website and traffic flowing all over the place to back-end systems, it's often difficult for engineers to find out where bottlenecks are and where all time is spent. Time could be spent at the networks, a database surfacing up all the data, or applications processing business logic. Today we're going to run a microservice architecture. The user will go to our website in the browser. The website will show our YouTube playlists, each playlist having videos. The website gets the playlists from a playlists API. The API gets its data from its own Redis database. For each of the videos in the playlist, the playlist API needs to gather the video data, so it calls the videos API, which has its own Redis database. It makes a call for every video in the playlist before sending the complete video catalog to the browser. If the system becomes slow, how do we find the bottleneck? Is the problem with the videos API, the playlist API, or the Redis database? Today we're going to be taking a look at distributed tracing and OpenTelemetry. Tracing helps us instrument our system so we can figure out where time is spent. So we've got a lot to cover, so without further ado, let's go. So if we take a look at our GitHub repo, we have a tracing folder, and inside the tracing folder I have a folder for applications, which is going to be all the applications that make up my microservice architecture. I have a Docker Compose file to start up all the applications, and I have a README. And this README is our introduction to distributed tracing, which is going to cover the example microservice architecture, what it looks like, the traffic flow, how to build the applications, how to run them, and how to access the application in the browser, as well as the traces. So be sure to check out the link down below to the source code so you can follow along. So let's take a look at our microservice architecture. So what we're going to do is run an application that returns playlists with videos in the browser. So we have our first applications, which is called Videos Web, which runs in the browser, which is a simple static HTML page running on an Nginx web server. Then we have a simple playlist API. So the Videos Web will make an API call to the playlist API to grab a list of playlists. The playlists contains a title, a description, and a list of videos. The playlist API will make a call to the playlist database, which running Redis, and that holds all the playlist information. And to add a little complexity to our architecture, we're also going to add a videos API, which holds all the data regarding videos. So here's an example of what a playlist looks like. It has an ID, it has a title, and it has a list of videos. Now for the playlist API to get the video data, it has to make a call to the videos API. So the videos API has its own database running Redis, which has all the data about videos. So if we take a look at the full application architecture, we have the Videos Web makes a call to the playlist API, which loads up all the playlists from its database. For each one of the videos in the playlist, it makes a subsequent call to the Videos API, which loads up the data from a videos database. Now, if you want to dive into the source code, it's very simple. On the left here, I have the tracing folder, and I have the applications Go folder here, as most of the applications are written in Go. So we have the Videos Web, which is a simple index HTML page, and a Docker file of how to run it. The Docker file is simply using Nginx, copying in all the HTML and CSS, and serving it up. The Videos Web makes a call to the playlist API, and if we take a look at that one, it's a simple Go application with a Docker file. And the playlist API will make a call to the playlist database. This is simply a Redis database, so I have a database file here that contains pre-built playlists. The playlist API will make a call to the Videos API, which is again a simple Go application and has a Docker file on how to build and run it. The Videos API also has its own video database, as you can see here, with another pre-built database file that contains all our videos. Then we also have a Docker Compose file, which helps us build and start all the applications on the same network. So you can see here I have a Docker Compose file, services, I have the Videos Web, playlist API, database, Videos API, videos database, and Jaeger that I'm going to show you in this example. Now feel free to try this out and have a look at the source code. To run it, The README shows how simple it is. All we do is change directory to the tracing folder, and then we go ahead and run docker compose build. And if I run that, that'll go ahead and build up all my container images. And to run all of it, all I do is simply say docker compose up. And if you're running this locally, just make sure that port 80 is available. So I'm going to go ahead and run that. That'll start up all my applications. It'll also tell me how to access the application. So I can just go to this URL on localhost. I can paste that in the browser, hit enter, and notice there's a bit of a delay and our application comes up. So you can see here's a bunch of playlists. And in each of the playlists we have videos. Now notice when I refresh this page that there is a couple of seconds of delay. Now from an engineering perspective, I would like to know where the time is being spent and what is causing this delay. If we have many services like the Videos Web, the Playlists API, the Redis, Videos API, another Redis, and possibly more, in reality, these services could be written in different languages, perhaps managed by different teams in different parts of the world. Therefore, we need a standard way of doing tracing. So this is where OpenTelemetry comes in. It helps us provide some standardized way of instrumenting our systems and producing traces. And that helps us measure application performance and find out where time is spent and where bottlenecks are. So what is OpenTelemetry? OpenTelemetry is a set of APIs, SDKs, and toolings and integrations that are designed for the creation and management of OpenTelemetry data, such as traces, metrics, and logs. So why do we need OpenTelemetry? Now I think we've covered most of the reasoning, but there's some good points down here. Firstly, it's vendor agnostic, so you're implementing an open standard. So if your company is using provider A for metrics and tracing, and they decide to move to provider B, you don't want to have to rewrite all your applications to change your instrumentation code. So OpenTelemetry provides some sort of standardization that companies can follow, making it easy to move between vendors. It's a single collector binary that can be deployed in many ways, so it's very flexible and dynamic. It provides an end-to-end implementation so you can generate, emit, collect, process, and export telemetry data. It gives you full control with the ability to send data to multiple destinations. It also provides an open standard semantic convention to ensure vendor-agnostic data collection. It's also important to know that OpenTelemetry is not an observability backend like Jaeger or Prometheus, but simply provides some standard open source practices of dealing with metric data. So in this demo, we'll follow OpenTelemetry practices to instrument our microservice architecture, and then we'll choose a supported backend system like Jaeger or Zipkin to collect our traces and visualize our traces as well. Now, in order to get traces from our applications, we have to instrument it using code. So if we take a look at the OpenTelemetry documentation, they have an instrumenting section, which talks about the facilities of instrumenting applications. So you can see OpenTelemetry provide a bunch of repositories for different programming languages. So they provide a core, which is the implementation of the OpenTelemetry API and SDK, and that is used to manually instrument an application. That's something we'll be doing today. And then they also have an instrumentation library, which contains all the core functionality plus automatic instrumentation for a variety of libraries and frameworks. For example, if you're running .NET and you're running a .NET web server, you might have some automatic instrumentation capabilities for instrumenting the web server itself. And then you can also use the core, which allows you to instrument manual functions and business logic. So in this documentation, they talk a bit about automatic instrumentation as well as manual instrumentations. And you can also see on the left-hand side here, they have all this different programming language support. So if we take a look at Go, they point you exactly where the current release of the library is. So in a bit, we'll take a look at how do we instrument our code. Now let's talk a bit about collection. Once we've instrumented our application and we're producing traces, we have to send it somewhere. That somewhere is a collector. Now the collector can be deployed in multiple ways. Now the collector contains a vendor agnostic way to receive, process, and export telemetry data, and it has some very good documentation. We take a look at the getting started section. We can see that it provides two ways of doing deployments. We can either deploy the collector as a single instance, running either as a sidecar or a binary on the same host or a daemon set, the applications will then point to that collector and send all the traces there. Or we can deploy it as a gateway, which is basically a standalone service, such as a container or a deployment. And that means you can have like one per cluster, one per data center, or have it running in some other region. So it provides a flexible way to deploy the agent. And they provide some good documentation on getting started with running it in Docker or running on Kubernetes. Now, if we click on the documentation link here, we can see they provide us a reference architecture. And here we can see an example of two types of collector deployments. So we have the application sending the traces to a collector on the same host. This could be a sidecar container, it could be a daemon set, or a binary installed on this machine. Or the application could send it to an external service running on another node, maybe one per cluster or region. So we can deploy this as an agent on the node or as a service. They also talk about greenfield environments and brownfield environments. So if you're testing this in a greenfield, you can use the OpenTelemetry collector as a deployment agent. Or if you're going to a more brownfield environment, you should be deploying a collector which supports many popular open source wire formats. So something like Jaeger, Prometheus, or FluentBit. So in this example, I'll be taking a look at a Jaeger deployment. Now, we spoke briefly about instrumenting to create traces from our application, as well as collection where we receive and process these traces. But what is a trace and what does a trace look like? When a service A calls service B, service A will look in the request headers for the trace context. The trace context holds tracing information and acts as the glue to link all the spans together. Service A can create a new span, which has a name and a timestamp of the entire network trace. It adds the span to the trace context and makes a call to service B. Service B receives the request, gets the trace context from the header, and may create its own span for whatever work it needs to do, like calling a database. It creates a span to record its overall work. It then creates a child span to record the database network call, and it gets its records back and creates another span to track the data processing. Finally, it adds the spans back to the trace context and sends it to a collector. All of these spans together form what's called a trace, which paints the picture of the workflow for service A to B. So the trace context is the glue that holds all the trace data together. It basically links all the spans and the services passes it to each other in the request headers. So it provides a common way of network calls to be traced. Now usually each service will add its own spans to the trace, and a span is a unit of work that has a name, a start time, and an end time. This could be a database call, it could be a call to another service, or it could be processing some business logic. The task of doing instrumentation is basically the task of creating spans to track any operation you want in your code. So let's take a look at our code to see how we can set up all these trace contexts and spans, and take a look at how we can visualize it in a system like Jaeger. So taking a look at a code example, let's look at our GitHub repo under tracing, applications go, and let's take a look at the playlist API first, since that is the first API that will receive traffic. Now web request will come from the video's web browser and hit the playlist API. So let's take a look at app.go, and this is where we have our code inside of a main function. So let's briefly run through the code, and I basically just set up and instantiate a collector. So I create this configuration object that connects to Jaeger on this port. I then create this tracer object called tracer, and I set it up using the Opentracing library as a global tracer. And then I proceed to define my business logic, and I have this router to handle GET requests on the root path. So any request to this playlist API will run this GET request code. Now the first thing I do regarding tracing is I create a span context, and I basically read the tracing context from the headers. I do this because there could be some services that do some instrumentation before it hits my service, so it's always good to read the tracing context first from the header and then extend it further. This is just in case the video's web is doing some instrumentation, or there's some proxy in front of my service that also does instrumentation. So I don't assume that this service is the first one to receive a request. So the first thing I do is create the span context, and I read the context from the headers. And the span context is something we pass down to subsequent functions that we want to instrument. So you can see here I create a span, and this is a span that will trace the entire operation of this GET request. So we start the span, we give it a name called /get so we can identify it in the Jaeger UI, and I run defer finish. This will ensure that the span finishes whenever this function is complete. I then proceed to add the span to the context, and I pass the context down to a function called getPlaylists. And if we collapse this function main, we can see here's the function called getPlaylist, and this is where the playlist API makes a call to the Redis database. And here I'd like to instrument that call to see how long it takes. So what I do is I start a new span from that context that we pass in, and I also do a defer span finish to ensure that this newly created span that I've created here finishes whenever this getPlaylist function finishes. So that's the reason for the defer statement. And then I go ahead and pass the context down to the Redis get call as well. So this child span will track the call to Redis and will be appended to the parent span. And then if we continue with the main function and we scroll down, we can see that once the playlist has been retrieved, we then loop through each of the playlists and loop through each of the videos inside of that playlist. And what we do then is make a call to the videos API to get each video data from the videos API and append it to our video catalog that we pass back. So I'd like to create another child span to instrument that work to see if there's any network latency between the playlist and the videos API. So I create another span like this by passing in our context, so that creates a new span, and I call this one videos API get since it describes the call that we're about to do. I then proceed to make a network request, and then what I do is I actually inject the context into the header and pass it along when I make a network call to the videos API. That means that the videos API can then read the trace context and proceed to instrument from there. So we'll have a view of the entire workflow, and then we say span.finish. So this is the playlist API. If we go ahead and take a look at the videos API, take a look at the app.go, we'll see a similar implementation over here. So firstly, we import all the Opentracing libraries as well as the Jaeger client. If we scroll down, we can see our instantiation of our configuration here, and we tell it where the Jaeger instance is. Similarly, we create a new tracer object and we set it as the global tracer. And here we have a separate route defined for handling the get call of the videos API. Now the videos API basically takes in an ID of the video and then calls Redis to get the video data for that video and return it as JSON. So the first thing we do here is create a new context and we get the information from the header. And remember that the playlist API would have injected the trace context into the header as well. So we receive that context over here and we're able to append new spans to that context. And then we start a new span to track our overall work for this web request. So I start a new span called /id get, and I say defer span.finish, which will finish the span as soon as this entire get request is done. And then what I do is create a new context here from that span. So I pass the span in and I pass the context to this video function. And this function is basically the function that's going to be making a Redis call to get the video. So if we proceed to collapse this main function, we can see here's our video function, and this is the one that makes a Redis call to get the video data. So you can see here it creates a new span from the context that we pass in, and we call this Redis get, and then we also finish the span. So we do a defer here, so the span will automatically finish whenever this video function is finished. And what we do here is we just do a simple Redis get by passing the video ID to Redis, get that video back, and if there's no results, we simply inject the span context back into the headers and return no results. But if there is results, we're going to basically return that video data, but we also inject the span context into the headers. So this is how we trace the code. Now, if we go to our tracing folder, applications go, we go to one of the APIs like the playlist API, and we scroll up to the main function, we can see that this is where we connect to Jaeger. So we connect to Jaeger on the address Jaeger and this port. And if we take a look at our Docker Compose file, we can see that we're also running Jaeger here, and we give it a container name called Jaeger, and that's how they can connect to Jaeger. And then also we've defined the public ports to connect to Jaeger on the user interface. So you can see in the Docker Compose file, I'm also running the Jaeger tracing all-in-one demo image. And this image contains all the Jaeger collection and the UI and all the stuff we need inside of one image. Now, this is not a Jaeger introduction video, but if you want me to do a deep dive on Jaeger, please let me know in the comments down below and we'll proceed to do so. And if we look look at the ports on this Jaeger image, we're exposing port 16686. And this is the port for the Jaeger UI. And if we take a look at our README, I've also put the link in here. So you can copy this link and go to the browser to access the Jaeger UI. So if we do that, we can hit the Jaeger UI automatically. We can search for our traces, and you can see we're getting two traces here already, the playlist API and the videos API. So we know that the playlist API is the one that receives the request first. So we click on that, we hit find traces, and we can see here we have our playlist API trace. So this is one single trace of a single network request. And that is me going into the videos catalog and hitting the enter button. And notice that there is a delay. So we want to find out where this delay is coming from. So if I go to the Jaeger UI and I click into this trace, we can see the entire length and all the network calls that's happened as part of this trace. Every single span is on the left hand side. So what we can do is if we go to the service and operations side here and we collapse all, we can see that this is our main span. So this is the first span we've defined in the playlist API, which is the main parent span. If I go ahead and collapse this one, we can see that we have next up is the playlist API Redis get. So this is the call that goes from the playlist API to Redis as a child span. We can see that it only took 2.6 milliseconds to return data from Redis. Then next up, we can see that the playlist API makes subsequent call to the videos API. So these are all the video API get calls that are happening, and you can see they're all relatively quick. If we expand one of them, we can see the videos API appending a trace to that. And this is the operation of the videos API. So we can see that the entire videos API operation took 2.7 milliseconds, but the playlist API outside took 5.8 milliseconds. So you can see where time is being spent by expanding all of these little spans. And if we expand that videos API get, we can see that this is the call to Redis. So Redis is taking 1.6 milliseconds for the result to come back to the videos API, and the remainder of the time is processing that data. The difference between this time and this time is obviously spent by the playlist API for processing that data before sending it back to the browser. So we can see each subsequent call to the videos API, and here is where the alarming bit comes. We can see the videos API get request happening here, and if we expand that, we can see that it's taking very long to get data back. It's almost 6 seconds. And if we expand that one, we can see the Redis call is really quick. So we're getting data from Redis really quickly, but what is the videos API actually doing on that get call? So now we can jump back to our code and we can actually go and look at the videos API. We go to app.go, and if we scroll down, we can see I've injected some dodgy code here that basically says if the video contains this ID and delay is true, then sleep for 6 seconds. So this is the delay we're seeing inside of the tracing UI. And if I go to the Docker Compose file and I go to the videos API, I basically get that delay from an environment variable. So this is code that I've injected to show you how you can track delays. Similarly, we can also track errors. So if I comment this out, and I create this flaky equals true, and we go back to the videos API app.go, I also have this environment variable that I read called flaky. And basically what I do is I just generate a random number, and if it's less than 30, I just say flaky error has occurred, which will cause a 500 server error. And if you go to the playlist API into the app.go section, and you look at where we create this web request, you can see here that if the error is not equal to null, we set this tag called error on that span. So that is telling the Opentracing library that an error has occurred. So it'll mark that span as an error. So what I'm going to do is I'm just going to stop everything for a second, and I'm going to say Docker Compose up, because we've now enabled that flaky environment variable. And then what I'm going to do is head back to my video catalog and refresh it a couple of times. And we can see that an error has occurred here. It's not rendering properly. And if we go back to our Jaeger UI, refresh, select the playlist API, hit find traces, we can now see that errors have come back. And if we click that trace, we can see there's 3 errors here, and it highlights where those errors have occurred. So this gives us good visualization into the network traces to look for delays as well as errors. So hopefully you have a better understanding on what Opentracing is and how distributed tracing can help you find bottlenecks in your microservice architecture. Now remember, all the source code is down below, so be sure to take it for a spin and learn about tracing. Now if you liked the video, be sure to like and subscribe and hit the bell. And also check out the link down below to the community page. And if you want to support the channel even further, be sure to hit the join button below to become a member. And as always, thanks for watching, and until next time, peace.